Thank you, Akio, for this very kind introduction. So good afternoon, good morning, depending on the part of the world where you are. So I'm very grateful to the organizers for the very kind invitation. It's really a pleasure to to give a talk in this online seminar. So as Akio introduced, I'm going to talk about several aspects of complexity of steady stationary incompressible fluid flows. These aspects includes topological stuff you will see, mainly related to knot theory, knots, links. Also dynamical complexity from a viewpoint of, of dynamical systems. And finally, also sort of computational complexity from the viewpoint of the theory of computation, Turing machines, indivisibility, and these sort of things. So I will give a survey on these on several complexity aspects that have been understood and studied in the last 5 years, mainly. Good. So, of course, if you have some questions or comments during my talk, I'll be happy to just please interrupt me. Maybe, I don't know, maybe you can chat or you can turn on the microphone and just ask me the question. Good. So let's start introducing the equations that describe the dynamics of fluid flow, which is ideal fluid flow. Ideal means that is inviscid, so no internal friction, no viscosity, and it's incompressible, the incompressibility condition. So these fluids, they are called ideal because they don't really exist in nature, but it's a good model to understand some aspects of fluid flows. They are described by the equations that were written down by Leonhard Euler already more than 150 years ago, the Euler equations. And they read this way. So the first one is the dynamics, the dynamical equation, the evolution equation for the velocity field. Here the unknowns of this equation is u. U is the velocity of the fluid flow. It's a vector field, time-dependent vector field, so it depends on time and space variable, x. And this first equation just describes, this is simply Newton's law, acceleration, which is this derivative of the velocity is equal to the force. In this case, there is just one force, which is given by the internal pressure, the inner pressure of the fluid. One could add other external forces, but in this talk, I'm considering just the pressure, the inner pressure, as the only force. And here in this equation, this balance equation, of course, the complicated term is this nonlinear term. U dot gradient U is a quadratic term. It's called the advective term. So it somehow means the variation of the velocity along the velocity itself. And the meaning of this mathematical term, it's simply this is a vector field. So it consists of 3 components, and each component is simply U scalar product with the gradient of the component K. So this is just the component K of this vector field U dot gradient U. And the second equation is just the incompressibility condition. The divergence of U is equal to 0. This means that the flow of the velocity field does not change the volume, the volume of the fluid locally, even locally. Good. So as I said, there are 2 unknowns in this equation. The main one is the velocity of the fluid. It's a time-dependent vector field, but there is also another object here, P. This is the pressure, which is a scalar function. Also depends on, in general, on time and space variable. And usually, once one obtains the velocity field, it's easy to compute the pressure just by inverting the Laplacian. Just if one takes the divergence in this equation, one obtains this other equation, minus Laplacian of P is equal to the divergence of this term, and then the pressure can be obtained just by inverting the Laplacian in the suitable functional space where you are. Good. So these are the other equations. But actually, as I said, as it said in the title of the talk, I'm considering just the steady situation, the stationary situation, stationary solutions to the Euler equations, which means that the velocity field, also the pressure, does not depend on time. So in this equation here, this time evolution equation, this term here is 0. U doesn't depend on time. So the Euler equation, in this case, you can write it down this way. Just the nonlinear term, the quadratic term, advective term U dot gradient U is equal to the minus gradient of the pressure, and the velocity field is a solenoidal vector field. Divergence of U is equal to 0. This is usually generally associated with equilibrium configurations. This is stationary solutions. Now, the velocity field is no longer time dependent. It's just an autonomous vector field in Euclidean space or on the geometry, on the manifold where you are studying the Euler equations. There is an equivalent formulation which is very interesting and very fruitful to study some properties. An equivalent formulation of this equation, which is in terms of the Bernoulli, the so-called Bernoulli function. This is also quite useful and quite used in engineering, and it's in terms of this function B, which is defined as P, the pressure, plus 1/2 U squared. This is called the Bernoulli function. And doing some analysis, some elementary computations and identities, one can write down in a completely equivalent way these equations in this other way, which is that the cross product, the standard vector product of vector fields U and curl of U, is equal to the gradient of the Bernoulli function, and the divergence of U is equal to 0. The curl is the usual curl or rotational operator in vector analysis. And the relevance of this equation is that it is very clear from this formulation that B is what is known as a first integral of the velocity field, also of the curl of U. It's or in other words, it's constant along the flow of U, because if you compute U dot gradient of B, here you multiply by U, scalar product, then this left-hand side term is 0. So this means that U dot gradient of B is equal to 0. So B is a conserved quantity of the velocity field, which in other words, I will explain this in more detail in 2 or 3 slides. In other words, this means that the velocity field lies on the level sets of the Bernoulli function. So it's a sort of laminar behavior in the case that the level sets of the Bernoulli function are surfaces and are differentiable surfaces. And here I want to emphasize that there is an object that naturally appears, is the curl of U. This has a name. It's very important. It's a very important quantity in fluid mechanics. It's usually denoted as omega, the curl of U, and it's called the vorticity. The vorticity of the velocity field of the fluid flow plays a key role. Mainly, this was discovered by Helmholtz in fluid dynamics. I will explain this later. One of the most important results related to this is the transport of vorticity. This is a stationary situation, so vorticity is not really transported. It's a stationary field. I mean, it doesn't depend on time, but it has some relations, some symmetry relation with the velocity that I will explain later. Mainly that it commutes with the velocity field, but I will introduce this in a few slides. Good. So I want to introduce. I need to introduce several objects that are very important in this talk. They are inspired. They follow the spirit of Lagrangian approach to fluid mechanics, because they are the integral curves, the orbits, the lines defined by solutions to Euler equations. So in this regard, there are 2 main objects here: vortex lines, streamlines. So vortex lines are the integral curves of the vorticity of the vector field omega. So they are defined by an ODE. Once you have computed the vorticity which is a solution to the Euler equations. In this case, it's a stationary solution, so it doesn't depend on time itself. One can compute, one can define the integral curves, the orbits of the vorticity via this ODE, and these are called the vortex lines. In the same way, one can define the streamlines. So these are the integral curves of the velocity field of the fluid flow. So they are again defined by this ODE. Here the interpretation of the integral curves of the velocity field, these streamlines, it's very clear from a fluid mechanics viewpoint. They are the trajectories followed by the fluid elements, the particle paths. In this case, in this stationary case, that the velocity doesn't depend on time, particle paths, streamlines, everything coincides. In this case, in the time-dependent case, they are different. Streamlines, the streamline pattern changes with time. It doesn't coincide with particle paths, but in the stationary situation, everything is the same. And there's another object which is quite important related to vortex lines, which is a vortex tube. In this case, a closed vortex tube, which is simply a solid torus, smooth solid torus, embedded in R3 Euclidean space that is union of vortex lines. So in dynamical systems words, this means that it's a domain that is bounded by an invariant torus of the vorticity vector field. So it's like a donut embedded in a space which is filled by vortex lines. This is a closed vortex tube. Let me show you some pictures to have a clear image in mind of streamlines, stream tubes, vortex tubes, and these things. So this is a bunch of streamlines. This you can understand this as an open tube. This is a cylinder, solid cylinder in space. This is another example of streamlines. These are 2D, two-dimensional examples. Streamlines, of course, may contain stagnation points, some equilibria, as is the case of this hyperbolic of this saddle type points, A and B. There are two other circular stable points here and here. And these are some examples of streamlines. You can think also as if these were vortex lines, for example, in the case that these are the lines of the vorticity instead of the velocity. This would be a vortex tube, a closed, an open vortex tube. In case this cap here coincides with this one, you get a closed tube, and this would be a vortex tube, a closed vortex tube. Good. And the vortex tube, so as I said, this has a very clear physical interpretation, a very clear picture. When you have fluid flow, somehow you can even see the streamlines, the fluid particle paths as the fluid is moving. You can also observe vortex tubes in a real fluid, and they can take they can exhibit very complicated shapes. They don't need to be a simple toroidal surface embedded in space. They can be even knotted, for example. So this is here. I show you a very nice picture of a vortex tube. This is of water. This was obtained more than 10 years ago by William Irving and his collaborators at the Irving Lab in Chicago. And this is a vortex tube in the shape of a trefoil knot. This is one. This is closed. I mean, this is diffeomorphic to a solid torus, but it's embedded in a space in a non-trivial way. And this shape here is called the shape of a trefoil because the core knot of this tube is a trefoil knot. So this can be observed and even produced in the laboratory. So these structures appear even in real fluids. So it's not only a mathematical observation or a bizarre object that one can obtain in theorems. Good. So now that I introduce very quickly the Euler equations and the stationary solutions, which are the solutions that I'm going to study in this lecture, the question that I want to address in my talk is how complex streamlines can be. And and not only individually. Of course, one can be interested in individual streamlines if they are knotted or they can be linked each other or these sort of questions. But in the union of all the streamlines, the general phase portrait of all the streamlines or vortex lines, and one can ask how do they fill the space. So this is somehow related to Lagrangian notions of turbulence, chaos theory, mixing properties of the flows. There are several other notions, Kolmogorov and many other notions of turbulence. It's quite unclear what are the connections of these different behaviors of fluids. But from a Lagrangian viewpoint, from a chaos theory viewpoint, it's quite meaningful and relevant to study this question, the complexity of streamlines and how do these streamlines or vortex lines fill the space. So let me summarize the problem. So we have, so from a mathematical viewpoint, one can think that we are studying vector fields in Euclidean space, say, or one can consider Euclidean space with periodic boundary conditions. This is the 3 torus. That satisfies vector fields that satisfy these 2 constraints. The second constraint is it's quite simple. It's just the solenoidal constraint, the divergence-free vector field. This fits within the theory of conservative dynamical systems. But the first constraint, this one, or equivalently this one, is much more complicated. It's a strong constraint on the velocity field, and one can ask which sort of dynamics is allowed by this constraint. If a vector field satisfies this, what's the dynamics of this vector field? The integral curves, the orbits of this vector field, can they form complicated structures, knotted structures, for example, or the union of these orbits can exhibit some chaotic behavior, ergodicity, these sort of things. This is the question. To understand which sort of constraints mainly this first equation impose in a flow, in a velocity field. Good. So here I want to first state a first observation, which is this sort of elementary classification of the stationary solutions of Euler equations, which is related to the Bernoulli formulation, the Bernoulli function. So you have 3 main cases in this formulation. The first one is when the Bernoulli function is not identically constant, it's not a constant everywhere. In this case, as I said, the Bernoulli function is a conserved quantity, is a first integral of the velocity field. So being a conserved quantity, a first integral, the streamlines lie on the level sets of V. So you have that the Bernoulli function, the level sets of the Bernoulli function, typically or generically, they foliate the space with surfaces. And then this leads to a sort of laminar behavior because the streamlines lie on these level sets of the Bernoulli function. This is the situation where B is not identically constant. But there is another situation which is related to the so-called Beltrami fields, which are vector fields that satisfy these equations. This is the definition of Beltrami field. They are vector fields whose curl, the curl of U, is parallel, is collinear with the velocity field itself. So curl of U is equal to F times U. F is some function that depends on space in general of U. The divergence of U is equal to 0. So this is a general Beltrami field. In this case, the Bernoulli function is identically constant because if you take, because curl of U and U are collinear. So if you remember the formulation, the Bernoulli formulation, if curl of U and U are collinear, if they are parallel, this is 0. So B is a function, identically constant function, a function which is a constant everywhere. So in this case, still there is some sort of laminar behavior when F is not a constant function. If F is not constant, because of this condition, the solenoidal condition, if you take the divergence in this equation, one easily gets that F is also a first integral of U. It's also a conserved quantity of the velocity field. So again, as before, U lies the streamlines, the orbits of U, lie on the level sets of the function f. So still, at least on the regular level sets, still this leads to laminar behavior. So this leads to the conclusion somehow that the most complicated, or one expects the most complicated behavior for a stationary fluid flow for the case of so-called strong Beltrami fields, which are Beltrami fields, so K of U parallel to U, collinear to U, but the proportionality factor being constant everywhere, which is simply this equation. K of U is equal to lambda U. Lambda is a constant. Well, generally non-zero constant. If it's zero, one would have the so-called harmonic fields. So one can think of non-zero constant. And in this case, there is no obvious first integral because lambda is constant everywhere. So streamlines of U don't need to lie on surfaces. This is a priori, in principle, compatible with chaos, with complexity, some sort of complexity, etc. So one expects these strong Beltrami fields will exhibit or may exhibit very complicated behavior from the viewpoint of the dynamical systems. Of course, one could have a mixing of behavior because one could have a Bernoulli function that is constant in some regions of space and is not constant in some other regions. So one could have, in principle, some Beltrami regions where you may have chaotic behavior and some other integrability regions. That's possible, indeed. But at least in some under some assumptions, for example, analyticity of the fields or some similar assumptions, you have this sort of classification of possible behaviors of stationary solutions of the Euler equations. And the point is that in 1965, so already more than 50 years ago, Vladimir Arnold made precise these considerations, and he stated a famous theorem on the structure of analytic stationary fluid flows, which is the content of the next slide. It's the famous structure theorem of Vladimir Arnold, 1965. And roughly speaking, here I'm not stating the theorem in a very precise way, but roughly speaking, it says that an analytic means C omega, so more than C infinity. So every the vector field admits at every point a Taylor expansion, which is convergent and converges to the field itself. So any analytic stationary solution of the Euler equation on a bounded domain omega with non-constant Bernoulli function is integrable. This is the content of Arnold's theorem. And integrable here means that the domain is divided, is covered by a union of finitely many subdomains, which are of these two types. Either the subdomain is covered by periodic cylinders like this. So cylindrical surfaces, the boundary of the cylindrical surface, which is the circle, would lie on the boundary of the domain omega. And the lines, the streamlines, are circular, they are periodic. The flow is periodic. So either you have this situation or you have this other situation. This you have to understand this as a closed tube, so as a torus, a toroidal surface. So you may have also this situation that the region, the subdomain is covered, is foliated by invariant tori of the velocity field, also of the vorticity actually. And the flow, the streamlines are, they define a vector field on each surface, on each of these invariant surfaces that is periodic or quasi-periodic. So all lines are either closed, periodic, or dense on the torus. So this is the pictorial representation of the cells that divide the domain omega, and this is the theorem that was proved by Arnold in this important situation when B is non-constant. So this somehow illustrates this heuristic consideration that I told you here, that one expects the most complicated behavior of a fluid, of a stationary fluid flow to happen when you have this particular class of solutions, these strong Beltrami fields, because in this case, the Bernoulli function is constant, is identically constant. So the case of strong Beltrami fields, also of Beltrami fields in general, is not covered by the structure theorem of Vladimir Arnold. Good, and here I want to show you an example, a very important example of a Beltrami field, of a strong Beltrami field, which is the so-called ABC family of Beltrami fields. This is in R3, but actually it's defined in terms of periodic of sinusoidal functions, sine and cosine. So actually this is defined, and this is understood in R3 with periodic boundary conditions, the three torus. And this family was written down by Arnold in his original 1965 article. And it has this very explicit and apparently simple expression. It depends, the family depends on three parameters, A, B, and C, real constants. Actually, if you compute the curl of U, this is equal to U. So it corresponds to eigenvalue 1, which is the lowest positive eigenvalue of the curl operator of the curl operator on the three torus with period 2 pi. And actually, the point is that even this apparently simple family of vector fields for some values, for concrete values of the parameters A, B, and C, they may exhibit, numerical experiments show that they exhibit a sort of complexity, high complexity in the dynamics. So you have chaotic regions, which means the existence of horseshoe type dynamics, chaotic invariant sets, also some regions of ergodicity, also some integrable regions in some sense. So even in this case, the dynamics of this family is quite complicated. Actually, there are many theorems. We don't know only numerics about this family. There are theorems that prove for some specific values or perturbations of A, B, and C, of the constants A, B, and C, that this vector field has positive topological entropy. And actually, all these considerations led Arnold to speculate on complexity of strong Beltrami fields. So what he wrote, what Arnold wrote in his original article, is this statement. It's let me read it. This is a literal translation. It was in French, the original version. So this is a literal translation. It says that typical strong Beltrami field probably displays streamlines with topologies as complicated as those of orbits in celestial mechanics. So this is not a very precise formulation or conjecture, because actually orbits in celestial mechanics, it's difficult to compare with orbits in this 3D fluid mechanics situation, because celestial mechanics usually involves many degrees of freedom. It's a very high dimensional space, the n-body problem. But in the same article, Arnold put this picture here, which is just to show what he meant by this consideration or this suggestion. And this is we can say that this is somehow a typical picture for a Hamiltonian system with 2 degrees of freedom. So it's a situation where you have some integrability regions here, but which coexist with some elliptic islands here, which are neighborhoods of elliptic periodic orbits, but coexisting with these hyperbolic periodic orbits. But the stable and unstable manifolds of hyperbolic orbits usually intersect transversely, and they create this structure here, which is the monoclinic tangle. It is the horseshoe. So it's chaotic sets. So this is a typical situation for a Hamiltonian system, and somehow one has to understand this Arnold suggestion as saying that typically generically strong Beltrami fields should display this sort of complex behavior. So this is a sort of mathematical problem that concerns stationary solutions, concretely Beltrami fields, which is this particular very complex class of stationary solutions. There is an intriguing observation, very interesting, probably should be studied more carefully in the future. And it's related to a phenomenon that is called Beltramization. This is, if you type in Google this name, Beltramization, there are several people who have studied this phenomenon. And there are some numerical studies, maybe even some experimental studies. And the phenomenon, Beltramization, it's the phenomenon by which velocity and vorticity of a velocity field no longer time independent. So this is even a non-stationary situation. So they tend to align in turbulent regions with low dissipation. So this consideration leads to the question of trying to understand what's the role of Beltrami fields in real physical turbulence. This is something that we don't know much about that, but it's simply I wanted to mention this because maybe there are some people in the audience more interested in the experimental aspects and in real fluid flows, not only these mathematical considerations, and maybe this Beltramization phenomenon can be interesting as a subject of study. Good. So now I'm going to start. So this was this first part of the talk where I introduce briefly stationary equations and some general stuff and properties about the stationary equations. Mainly, probably the most important result about steady states is this Arnold's theorem on the integrability of steady states when Bernoulli function is non-constant. And I also wanted to emphasize this possible complexity of Beltrami fields, which are not covered by Arnold's theorem, Beltrami fields, and also this speculation, this suggestion by Arnold that Beltrami fields indeed should exhibit typically a very complex behavior. So now in the second part, I'm going to revise several results in the literature that we obtained recently about complexity, topological, dynamical, computational, on stationary solutions, actually Beltrami fields. But before, if you have some questions or comments about this first general part or consideration, just you can ask me, or otherwise I continue. Good. So let's then start with this. I don't know, probably you cannot see this top part. I cannot see it actually because there is this part. I don't know how to.
Now I can see it.
You can see, okay.
Yes.
Very good. Okay, great, because actually my screen it doesn't appear. Okay, good. So okay, the first part, it's topological complexity. That actually concerns individual lines, streamlines or vortex line, just one or a few of them. So this one can think of this problem as first motivated, or I wouldn't say stated, but yeah, probably the best word is motivated by Lord Kelvin. His theory in 19th century, his speculation that each atom is a stable, in some sense, knotted vortex tube in the ether. So at that time, the 19th century, second half of 19th century, it was believed that the ether exists. It's a sort of fluid that covered the universe. The fluid, it has no friction, so it could be modeled, it's incompressible, etc. So it could be modeled by the Euler equation, by the Euler equations, actually. So the interest of Lord Kelvin was trying to understand why there are what an atom is and why there are different atoms corresponding to different elements, lithium or hydrogen or oxygen or whatever different elements in the periodic table. So a very ingenious theory of Lord Kelvin was that each one of the atoms, each one of these atomic properties was related to the knot type of the atom. The atom would be a vortex tube in this fluid, in the ether, and depending on whether you have a trefoil or you have an unknot or you have a Whitehead knot or whatever, then the atom would have different atomic chemical properties. It would correspond to different elements. Okay, so this was a speculation of Lord Kelvin. Of course, this turned out to be completely wrong because the ether doesn't exist, and it's not atoms are totally unrelated to vortex tube of a fluid, etc. But this remains as an interesting question, has been revisited. So it was here I want to mention Keith Moffat work, some of his works. It's in 1985. He used the mechanism of a very interesting phenomenon that I'm not explaining today, the so-called MHD relaxation, magnetohydrodynamics relaxation, to suggest that there could exist Euler steady states with string tubes of arbitrary knot type. So the idea of Keith was you have an initial datum for the ideal MHD equations, which is a solenoidal field exhibiting some string tubes of some complexities and not some topology in the streamlines, actually of the magnetic field. This is not the velocity field, it's the magnetic field. And then after relaxation, and if there is some limit, etc., then one could get an MHD equilibrium, which is actually equivalent to a stationary solution of Euler, which would exhibit the same sort of complexity. But Moffat, Keith already pointed out that typically, or one should expect that this relaxation phenomenon leads to discontinuities in the limit. Discontinuities meaning that the solutions that one gets in the limit, they are not really smooth solutions. They could be what are called weak solutions of the equilibrium equations, or not even continuous, could be just L infinity or even L2 or whatever. So of course this could lead the presence of these discontinuities, which actually is very interesting because it's related to other proposals in the literature in plasma physics to explain heating of solar corona by Jim Parker and some other people. This should lead to no preservation of topology. So then it's difficult to use a relaxation scheme, although there have been, after Keith's works, there have been a lot of studies in this direction, changing the equations, not considering the MHD equations, but other relaxation mechanisms. But it looks difficult to use a relaxation scheme to construct smooth steady states with prescribed topology. This is not impossible, but simply it looks quite complicated. So what we proved, the first theorem that I want to state today is that following an approach that is purely stationary, I mean just working with the stationary equation of Euler, more concretely with the Beltrami equation, curl of u equal to lambda u. So it is not at all a relaxation scheme. Simply, it's a sort of partially it's related to elliptic PDEs tools, although not only, because actually Beltrami equation is not elliptic, but it's related to that. We proved already almost 10 years ago with my colleague Alberto Enciso the following realization result for vortex tubes, string tubes of steady fluid flows. So the result that we prove is that if we have a finite collection of toroidal domains in R3, pairwise disjoint toroidal domains in R3, T, let's take any one. So for let's put some picture here. You can take only one toroidal domain like this, trefoil toroidal trefoil tube, or even you can take a Borromean configuration as this, or any other configuration of nodes or links. If you take this, then there exists a deformation of space, a diffeomorphism, such that the deformed collection of tubes, you deform the collection. The original collection is not realized, but you can deform it with a diffeomorphism, a continuous motion of space, such that the deformed object, which still has, of course, the same topology as the original T, is a collection of vortex tubes of a steady fluid flow. Actually, which satisfies the question curl of u equal to lambda u for some non-zero constant lambda. And of course, since vortex tubes are the same as string tubes for Beltrami fields, because curl is parallel to velocity, Then this is also a collection of string tubes, not only vortex tubes. And actually, these solutions decay in the best way that a Beltrami field can decay, which is as the inverse of the distance to the origin. This is the best decay of a Beltrami field. In particular, Beltrami fields do not have a finite energy. They do not have finite L2 norm. They cannot have any Beltrami field, not even with non-constant proportionality factor. This is a big problem. Then I will, at the end, the last slide will be about open problems. One will be related to the question of proving this sort of theorems, of realization of not theorems for finite energy solutions. That's a big problem. But even they do not have finite energy, they are not extremely bad because they are bounded. In particular, they decay. It's the best one can have with this approach, with a Beltrami field. And a remark is that an analogous result hold in the compact setting, not in R3, in R3 with periodic boundary conditions. So this means the 3 torus. On T3, here you have the same similar result. These are solutions with finite energy, but no longer on the whole R3. Solutions with finite energy on T3, on the 3 torus, R3 with periodic boundary conditions. So this is the first result that we prove. So this shows that from a topological complexity viewpoint, one can have stationary solutions that exhibit vortex tubes, actually also vortex lines, stream tubes, stream lines of any knot or link type. That's a first observation. So, the first conclusion from the topological viewpoint is that there are no restrictions, no obstructions on topological complexity for steady fluid flows. Okay, that's the first observation. Any knot, any link that one can consider can be realized as union of vortex lines or stream lines, vortex tubes, if you have toroidal domains, string tubes in a steady solution of the Euler equation in R3, and these solutions are Beltrami type, or Beltrami solutions. Good. So this concerns this topological complexity, but of course this is a sort of poor understanding of the vector field, because this is just one line or a bunch of line or even a bunch of invariant surfaces, which are these toroidal surfaces. So it's quite relevant to understand, for example, how complex stream vortex lines are inside the vortex tube of non-trivial topology. Can they be chaotic? So we know with this realization theorem that we prove that we can have stationary solutions with a vortex tube or string tubes having this shape. So you have an invariant torus, an invariant tube with this trefoil shape, but we don't know what happened with the lines, with the vortex lines, with the stream lines inside the tube. Are they chaotic or they are integrable in some sense? What's the situation here? So this is the content of the second study, the second result that I'm going to state, which is trying to understand dynamical complexity from the dynamical systems viewpoint. Here, dynamical refers not to time-dependent Euler equation. Still, we are always on stationary solutions. This refers to the bunch, to the union of all the stream lines or of all the vortex lines. The phase portrait usually is called usually in the literature of dynamical systems. That's why I'm calling dynamical complexity from the viewpoint of dynamical systems. The whole phase portrait of the velocity field or the vortex field. So a standard tool to analyze the dynamics of a flow, usually a 3D flow, and which is the case here, of course, is the Poincaré return map on a transverse disk. So if you have a flow and you have a disk that is transverse, one can define a map that assigns to each point of the disk, you follow the flow, and it gives you another point in another section in R2. And this map, one can check that this map is area preserving because U is solenoidal, it is a diffeomorphism. So this Poincaré return map on a transverse disk is a main tool to analyze the dynamics of a 3D vector field. And for example, just to show you how this Poincaré return, how chaos or a sort of chaos is reflected in Poincaré return maps, we have that solenoidal 3D field is chaotic, well, in a very light way, in Devaney sense, but okay, in some sense, it's chaotic, if and only if it exhibits horseshoes. And horseshoes means that the dynamics on the, if this is a section, this is a section, is a disk, a transverse section, then that there is a Cantor set, a transverse Cantor set that is invariant by the iteration, by this Poincaré map, and the map and the dynamics on the Cantor set. This is a square Cantor set, Cantor times Cantor, and the dynamics in the square Cantor set, it's in some sense like a shift dynamics. So it's a chaotic in the 3D. When you consider this object in 3D, is a chaotic invariant set whose transverse section is not a simple surface. The transverse section is a Cantor set, so it's a complicated object, and it has positive topological entropy and some complex and hyperbolic behavior, etc. So this object is very important, this Poincaré map, to study the dynamics. And the second main result that I want to introduce in this lecture is a result that I obtained recently with Pierre Berger and Anna Florio, both in Paris, the University of Paris, and it's related to the concept of universality. So this is a result. This is a concept that was introduced by Dima Turayev in early 2000s, and roughly speaking, the definition of universality of a flow is the following. It says that solenoidal vector field is universal if somehow, if you can find any transverse dynamics in some Poincaré section, or more precisely, if any area preserving the diffeomorphism of the disk can be approximated by the Poincaré return map at some transverse section. So this means that you have your vector field in a space, and if you can find some transverse disk, then it means that for any diffeomorphism of the disk that one can imagine, one can find a transverse disk such that the return map to this transverse disk is almost this given diffeomorphism. So it contains somehow, that's why I call this slide one Beltrame flow to rule them all, a single vector field, which is the statement of this theorem, contains every possible up to arbitrarily small error, contains every possible dynamics, every possible transverse dynamics. So the theorem that we prove is that there exists an open set of Beltrame fields in Euclidean space with infinity topology, such that a generic element of U is universal. These Beltrame fields exhibit sharp decay at infinity, and so this means that they decay as 1 over x, and it implies in particular that a single Beltrame field of this set contains all possible transverse dynamics. So in particular, this strong version of Arnold vision. So remember this picture of Vladimir Arnold in his article. He showed he drew this picture in his article of this transverse dynamics. So the theory in particular says that if one takes this diffeomorphism, there is a Beltrame field that contains precisely, or at some transverse section, this picture. Okay, up to error, but this picture is robust because of Kean theory and some other dynamical systems tools. So this picture is preserved by a small error, by a small perturbation. So this means that this is contained in a Beltrame field, actually in a generic Beltrame field of some open set, which is the open set of this theorem, stated in this theorem. Okay. So in particular, they are chaotic. All these vector fields are chaotic. They have positive topological entropy. Good. So this is the second sort of complexity that I wanted to introduce in this talk. So let me summarize these two sort of complexities. The first one concern just individual lines or individual tubes. We said that any topology of an individual tube or line, or even finitely many of them, a link, can be realized by a Beltrami field. You can find a Beltrami field that contains these objects. This is possible, this exists. The second sort of complexity is that there are Beltrami fields, actually a locally generic set of Beltrami fields that contain this picture. Actually, not only this picture, but any other picture of any diffeomorphism of the disk that one can imagine, up to error. So if the picture is robust, then you will observe the same dynamics in the field. If it's not robust, then not necessarily. But if it's robust, yes. But in particular, this picture can be observed in a locally generic set of Beltrami fields. So this is dynamical in the sense that this is saying something about the phase portrait in this region of the field. It's not only individual lines, it's the union of all these lines. You have chaotic regions, you have hyperbolic orbits, you have elliptic islands, you have integrability, quasi-periodic regions, etc. The third sort of complexity that I want to present here very briefly, because time's running and I think I have 5 more or less minutes left. It's a sort of computational complexity, which is related to one of the most popular mathematical descriptions of a computer algorithm, which is a Turing machine. And we have the notion of universal Turing machine. That is a machine that can simulate, in some sense, any other. So, as I said before, while nodes or links represent somehow a measure of this individual topological complexity, and chaos is somehow a measure of dynamical systems complexity, then the ability of a dynamical system to simulate a universal Turing machine, in some sense, that I'm going to make precise soon, is a measure of computational complexity. So for topology, we have nodes. For dynamical systems complexity, we have chaos, horseshoes, entropy, etc. For computational complexity, we have universal Turing machines and simulation of universal Turing machines. So in this regard, Chris Moore asked in 1991 if there exists fluid flows solutions to Euler that can simulate any computer algorithm. So, so in this sense, I need to say what's the meaning of simulation or the meaning of a Turing complete system. So if we have a Turing machine, so a Turing machine, I'm not, let me see, I'm not defining in a precise way. You can understand a Turing machine. Well, it's an algorithm, of course, so a sort of computer program. You can understand actually from a dynamical systems viewpoint as a dynamical system in the set of sequences, acting on the set of B-infinite sequences. So there is the notion of universal Turing machine. A universal Turing machine is a Turing machine that can simulate any other Turing machine. There is a coding and decoding procedure that allows you to simulate any other with this single universal Turing machine. And we say that the definition of Turing completeness is that a vector field is Turing complete if given any input tape. So the input of a Turing machine, it's a tape, it's a sequence of zeros and ones, a B-infinite sequence of zeros and ones. Then if for any input, there exists a point in a space, computable point, and a computable open set, such that the orbit of X through P intersects U, the open set, if and only if T halts. T stops with starting with such an input type. So this is the notion of simulation. Somehow, it's you say that you are simulating with a dynamical system a Turing machine, in this case a universal Turing machine, if for any input tape you run the Turing machine, and if it holds, the corresponding point of the dynamical system intersects a certain open set. If it doesn't hold the Turing machine because it goes into it could be like a shift, for example, or it could be like a loop or something like this. If it never holds, then the orbit never intersects such a set, and everything is computable, the open set and the point, and somehow you are following the steps of the Turing machine, following some particular trajectories and points in the phase space of the dynamical system. So this is the notion of a Turing complete dynamical system, and somehow you can understand this as in the way that you have embedded somehow the Turing machine into the flow of the vector field, and this is this important concept. And the theorem that we prove with Robert Cardona and Eva Miranda from Barcelona is that there exists, again, Beltrami fields, these sort of stationary solutions of Euler equation, which are very complex in Euclidean space, that can simulate a universal Turing machine. So they are Turing complete in this sense. So there is a universal Turing machine that can be embedded, whose dynamics somehow can be embedded into the dynamics of a Beltrami field of a steady Euler flow in Euclidean space. All the computations, the Turing machine actually is embedded into an invariant plane. It's not three-dimensional, it's embedded into an invariant plane. And okay, the point of this, the bad point of this Beltrami field is that it doesn't decay at infinity. In particular, it doesn't have finite energy, and it's not even bounded. It's a vector field which has, in general, a very fast growth at infinity. Okay. So an interesting corollary, and I'm finishing this and one slide more, is that since the halting problem is undecidable, a very interesting corollary is that there are undecidable trajectories of such a Beltrami field in the following sense. There is no general algorithm to check whether the trajectories of this vector field starting at certain initial points will intersect a certain open set. Certain meaning computable, and this is the meaning of indecidability here. One cannot decide whether the trajectory of the dynamics will reach some open set, and the decision problem is, of course, from a computational viewpoint. There is no Turing machine to decide this reachability problem, this reachability property for all of this initial data in such a set. So this is the existence of these undecidable trajectories. This is the most interesting corollary of this result. And here I have a few slides about some ingredients of proof, but I'm skipping this. So I wanted to finish with some open problems that are interesting in this setting. So summarizing, we have used Beltrami fields to construct stationary incompressible fluid flows that exhibit topological complexity. This means, remember, they exhibit nodes, links of any topology, of any complexity, not topology. They exhibit dynamical complexity in the sense of the phase portrait. One can embed any transverse dynamics in a Beltrami field, in particular this picture of Arnold exhibiting chaos, elliptic islands, etc. You can have this in Beltrami fields, actually in generic sets of Beltrami fields, and also this computational complexity in the sense that there exist Beltrami fields in Euclidean space that can simulate universal Turing machines, and they exhibit then these undecidable properties, undecidable trajectories. But the bad point of all these solutions in R3 in Euclidean space is that they don't have finite energy. The point is that they are Beltrami fields. There are no Beltrami fields with finite energy. So this leaves open several outstanding problems. So, for example, a first question is if there exists steady states with a compactly supported vorticity, not only finite energy, but compactly supported vorticity of arbitrary topology, of arbitrary node type. And these steady states as smooth as possible. Okay. We constructed steady states with vorticity of arbitrary topology, arbitrary node type, but the vorticity is not confined to such a region. It's an analytic field. Actually, it lives everywhere. It's an invariant region, an invariant torus of the vorticity, an invariant vortex tube, but the vorticity is not compactly supported in such a region. A second question is related to this computational complexity. The problem is if there exists finite energy in R3, finite energy solutions that simulate a universal Turing machine. This is complicated. Well, both this and this are very complicated because then you cannot longer use Beltrami fields because they don't have finite energy. So, and we don't know much about steady states that are not Beltrami fields. We don't have many tools to construct them. A third question, it's more dynamical. So what are the instructions for a solenoidal vector field to be diffeomorphic to a stationary solution of the Euler equation? So this means, or this is asking for a comparison between a general solenoidal field and a general steady state to understand the phase portraits. And finally, this is a relation trying to look for a connection with time-dependent Euler equations. How do these properties affect the stability in some sense of these solutions in the context of time-dependent Euler equations? Good, so I think I'm finished. So thanks a lot for your attention.